Minimum embedment depth comes from a variety of conditions. Embedding below the frost line to avoid frost heave, enabling the removal of the topsoil organic layer, avoiding erosion and scour from water and wind, realizing the full bearing capacity of the soil, and realizing extra capacity from passive pressure or skin friction. Now, embedment depth of main structural components will always be a trade-off between labor and structural capacity. For example, ramp wall and extra access ramp embedments should be minimized to reduce excavation while maintaining the full bearing capacity to reduce the risk of settlement or bearing failure. The same trade-off occurs with anchor embedment. A shallow anchor will reduce the ability of the anchor to act as a shear key and will reduce skin friction or sidewall friction capacity. For the foundation, we are most concerned about getting our full bearing capacity while minimizing excavation. So in later lectures, we will discuss how to actually calculate this bearing capacity, which is a function of the foundation embedment depth. So I've drawn a few rudimentary diagrams here showing, the passive pressure and skin friction that can occur between the anchor and foundation. And our first stop in this lecture is going to be the IBC section 1809.4, which cites the minimum depth of a shallow foundation shall be no less than 12 inches or 30 centimeters below the undisturbed ground. This should be altered based on frost depth in section 1809.5. But we will consider adjustments for frost depth in another lecture on cold weather conditions. And there is no specific information on masonry walls or gravity anchor beams, but we can extrapolate this information from the shallow foundation requirement to set a minimum, not necessarily a recommended, but a minimum embedment depth of 30 centimeters for the anchors, ramp walls, and extra access ramps. This minimum is to realize full bearing capacity of the soil and minimize any differential settlement that would lead to cracking and loss of capacity. Specifically regarding foundations, bearing capacity, like we mentioned, is more of a concern, especially in 3-tier abutments or 3.5-tier abutments. There is more exposure to any scour from water runoff and wind, and further research beyond the 30 centimeter IBC minimum would suggest that embedment up to 100 centimeters is the minimum for shallow foundations based on soil type, specifically in high plasticity clay soils. So for a sanity check, we can use the Rankine formula to calculate the minimum shallow foundation depth for, say, a typical EIA soil. And here's the Rankine formula. Embedment depth, our minimum depth, is going to be our surcharge over our density of the soil times our 1 minus sine phi over 1 plus sine phi squared. And phi being our angle of internal friction, 30 degrees. Our density of our soil will take as 1,800 kilograms per cubic meter. And our p-value here, sorry, that's not our surcharge. It's going to be our assumed bearing capacity of the soil. In this case, we'll take as 3,000 psf or 14,650 kilograms per cubic meter per square meter. And then rearranging with the appropriate units, we'll get a minimum value of 0.9 meters. So comfortably, we can set our foundation depth requirement to a minimum of 1 meter. A summary of minimum embedment depths of structural components is provided in the EIA Bridge Binder Volume 2. And of course, this is a value that depends heavily on the properties of the soil. So in this case, we're doing it for the initial assumed properties of soil we have for our sites, but this value can and should be adjusted if we are learning more or concerned about soil type and soil properties on site.